Hello, lesson 8.2, more on confidence intervals. So, a quick review. How in the world do we set up a confidence interval? Well, the point estimate is the middle, and then there is a margin of error on either side. So, I could say I'm going to shoot 20 free throws, and my point estimate is I expect to make 12, and then that's the point estimate. And then I could go up three maybe or down three. I'm just making this up. So up three would bring me to 15, down three would bring me to 9. So my point estimate would be 12, and my margin of error would be 3. And the interval itself would be 9 to 15. I, I'm 95% confident that I would make between 9 and 15 of my free throws, as an example. So this activity, we're going to really just use an applet um, to explore like these confident intervals, especially like 95% is a pretty common one. So this applet, you don't have to type it in. It is in Schoology, okay? Um, and I'll open that in a moment. But it will over and over make um, it will make a bar like this to represent the confidence interval, and the point estimate will be a dot in the middle, and it'll have a line on either side. The line on either side is the margin of error, okay? So in Schoology, here's how where you can find it in the lessons folder, the link for 8.2 lesson applet. Okay. Um, and let's see what we're supposed to do with it first. Um, it says use the default settings of 95% and a sample size of 20. So what's happening is um, okay, that's the default, is that they're creating a 95% confidence interval, and they're taking a sample size of 20 different data points. So when I click sample, you'll see those 20 gold dots. Those are the 20 random data points collected from the population. The black curve, the more lower curve, is the population, and the red dotted curve is the sampling distributions shape. They're both normal, but you can see the red one is actually um, more tightly grouped and has a lower standard deviation. Anyway, if you hit sample again, you get another sample with 20 gold dots, and the black dot in the middle is the point estimate. And then the little line going left and right represents the represents the margin of error. So the black dot, so these black dots, they all represent the point estimate from that sample, okay? The point estimate, or X bar, from that sample, okay? And then the margin of error is how long each bar is going either way, okay? On the left and the right of the black dot. Now, I do want you to notice something. If you keep hitting sample over and over, the black dots are moving, right? But what's not changing is the margin of error. And this does connect to what we learned yesterday, because the margin of error is based on um, two standard deviations, because we're doing the 95% rule. And standard deviation is sigma divided by the square root of n. And all of your samples have the same n, the same sample size, and they all have the same um, standard deviation. the black curve is where we get sigma from. That's the population, and it has a sigma, a standard deviation. So what I'm trying to say here, and very long-winded, is the length of these intervals all match because this is the same for every single one. If I go back to the applet and do it in real time, you can see this. If I keep hitting sample, 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 I'm getting 20 new gold dots each time. They each have their own X bar. That's why these black dots are moving all over. But as I create them, you can notice the length of the intervals are all the same, which is really, really noticeable, really important. And you can keep doing that, okay? Um, then you can see here it says hit 13 and the hit percentage is 100%. What it means by hit is that the green line represents the true parameter, okay? And is the true parameter, is it captured inside the interval? So on this first one, the green line, it's actually really, really close to the point estimate. So it's definitely contained in the interval. It's contained in this one, and this one, and this one, and then the red one missed, right? The green line went to the left of it. So this interval was too high, largely because all the gold dots were way too high and the point estimate was too high. So it wants us all to do this. Keep hitting sample, or you can actually do 25 at a time until we have a total of 1,000 samples. We want to know how many of them hit and what percentage hit. So let me do that, and you do it as well. I'm going to reset and just start over. Again, if I do one at a time, you can see, and it's doing 20 dots at a time. You can keep going maybe until you find one that misses. Now, it's not likely to find one that misses because, oop, there, I got one. It's not likely because the confidence level is 95%. All right, let me reset and go faster. I'm going to do 25 samples. Boom. One of them missed. And then, boom, 25 new samples. But it is doing a cumulative tally as I go. It's, oh, there, that one had 3 reds, so 3 of the 25 intervals did not capture the mean, the true mean. It wanted us to do this, the notes, until I get to 1,000, so I'm doing high repetition over and over and over. This one, look at that, all 25 of them worked. That's cool. Keep going until I get to 1,000. You do the same thing. Whoa, there we go. So hit for me is 956. Okay. How many hit? 956. What percentage is that? Well, 956 out of 1,000 is 95.6%. Wow. So interpret this. Well, 95.6% of the intervals captured the true mean. 95.6% of our samples created a confidence interval that captured the true mean. So this is another way to think about what the percentage means. The confidence level percentage. If you want to be more confident, if you want this percentage to be higher, right? You want it to be like 99. Well, the only way that's going to happen is if your intervals get a little bit wider. Like this red one right here was pretty close. But if I were to lengthen this and this, the margin of error, it would catch. And the way to lengthen that is to increase the percentage to 99, perhaps. All right, now we're going to just play around with this slider. Let's adjust the confidence level up to 99, 99 and a half, and what happens to the intervals. So let me just change it. Bloop. You can see there's 97, and they got longer. 99, they got even longer. What if I go the other way? What if I go down to 90? They shrunk. You can go down, how low can I go? 83, 81. You can see those are very, very narrow intervals now. And it automatically updated my 1,000 trials right there. So you can see I hit 815 times out of 1,000, which is about 82% or 81.5%. So increasing the confidence level widens the interval, okay? Which is what number 4 is saying right here. We went from 95 to say 99, the intervals increased in length. In order to raise your confidence that the parameter is captured by your interval, you would have to increase the length of your interval. So the shortcut or the end of the final takeaway is this, that your confidence level goes up, your interval length goes up over and over. If your confidence level goes down, your interval length goes down. What about sample size? If I change sample size to more, what happens? What's going to happen to the interval? Well, you can think about this, right? What's going to happen if n gets bigger? If n gets bigger, this standard deviation gets smaller. So I'm predicting that these margin of error on either side will get smaller, which will shrink my intervals. So let's see what the applet says. Let me reset. I'm going to increase. Well, here, let's do a couple more with 20 dots. There you go. 20 dots, sample size of 20, 20 random data points, get an average. What if I go, boom, 40, and start over? Oh, let's see, can you keep those straight? It looks to me like they're not as long, right? What about 100? Ooh, there's 100 gold dots smushed together, but you can see that the length of the interval is shrinking. It's going down, okay? The notes wanted us to increase it to a sample size of 250. Okay, let's see if I can get my slider to 250. Oh, that's all the way over. Um, Let me just say, look at the red dotted line, the red normal curve here, as I increase sample size. There it is now. There's 40. The red dotted curve got a little bit taller and a little bit more tight, smaller standard deviation. 75 got tighter yet. 150, look, it's really getting closer and closer to that green line. 200, the standard deviation is shrinking. Um, so 250. If I hit my samples, look at those. Look how small that interval is. And this should make sense, you guys. Look at it. Like if I go back to here, right, with my standard deviation, if I had a standard deviation for a population, I yesterday our test score standard deviation was 6.8. If I had a sample size of 5, like I did yesterday, that would be the standard deviation of that sample of size 5. If I increase my sample size to 250, like I just did on the applet, whoops, I multiplied. If I do that, look at that. The standard deviation is now 0.43. It's like it's over 6 times smaller than 3. So it will shrink my intervals because remember, I'm always taking my point estimate and I'm going up 1, 2 standard deviations and down 2 standard deviations. That will always be the general rule of thumb to create a 95% confidence interval. Okay? Um, so it wanted me to do this again. It said create another 1,000 samples. And what happened to the intervals? Well, they got shorter because increasing sample size reduces the variability, it reduces the standard deviation. I'm going to do the clicks here. They want me to get to 1,000 samples. Keep going. Well, I'm at 1,003. Okay, and let's see, it's kind of small. That's better. You can see that I set my confidence level to 98%, and look at that. I hit 986 out of 1,003 for pretty much spot on 98% success. Um, so you're learning here that if you really want to raise your confidence, you can increase your sample size. Okay? And what's happening is as n gets larger, I suppose this would be what comes first. As n gets larger, your standard deviation goes down. And because your standard deviation goes down, your margin of error goes down. So your intervals are getting narrower. Okay? This little diagram students have found helpful in the past. It's kind of like a funnel approach, but the higher confidence level goes on the top and the lower confidence goes on the bottom. And this is just a visual for showing you that a 99% confidence interval is wider than a 95%. Because if you are more confident that the interval captures the truth, you will make it longer. Okay? And if you're less confident, well, then um, you can make that interval shorter. All right. So interpreting the confidence level, this is what we were kind of doing right here, right? We made 1,000 samples. We set it at 95% confident, and we ran 1,000 samples. And so this is what we found to be true for those 1,000 samples, that pretty much 95% of them created intervals that captured the true mean. That is interpreting the confidence level. If we were to make many random samples and construct intervals for each one, about blank percent of the intervals would capture the parameter. And 95% is the most common, but you can really make any percent that you want. I mentioned these earlier, okay? If you increase your confidence level, the margin of error goes up, which makes your interval wider. And if you increase the sample size, your margin of error goes down. Margin of error accounts for sampling variability, aka variability. Remember, this is sigma or standard deviation, okay? It does not do anything for non-response, undercoverage, and response bias, okay? It can account for people that did not answer the survey. It cannot account for people that, by the sampling method, were not included in the sample, okay? And if people are answering questions because they're being influenced to answer a certain way, the margin of error doesn't know that. So the margin of error can only take into account sample size, which is going to affect the standard deviation. All right, I want to show you one more thing that is kind of interesting. If you go to the stats applet, let me just do this one more time from scratch. There's also an interactive applet here called in concepts called Simulating Confidence Intervals. See it right there in Concepts. And if that first applet wasn't doing it for you, this might. You can make your population normal. You can actually do skewed, bimodal, and so on, but I'm going to just leave it at normal. And this population is centered at 10. So you can see mu is 10, and the standard deviation lines are going up by 2. Now, we can take a sample. In this case, I'm setting my sample size to 30 data points, and I'm computing a 95% confidence interval using that sample. We'll get into the weeds about these three things as the year goes on, but for now you could say Z distribution with sigma, because that's what we're familiar with. And again, I could change the percentage to anything I wanted, and I could change the sample size to anything I wanted. Let's just leave it here for now and hit go. So it showed you the 30 random data points, the dots. It showed you for those 30 dots X bar. It got 9.786. So it was below the parameter because the parameter is 10. And it showed you S of X 1.858. Okay. The standard deviation for that sample. The confidence interval it created is also listed right there, 9.071, 10.502. And it placed it right here, kind of on this little make-believe vertical plot here. The dotted line at 10 is showing you where the parameter is, and then that interval it just found is the green line. You can quickly do more. You could say, well, do that again. Do that 10 more times and compute a confidence interval for each one. Now hit go. And so it did it 10 times. Now it doesn't show you all 10 of them up here, but I think it shows you the most recent one. I think it's showing you right there, the one on maybe the very top, actually, the highest one. Okay, if the interval is green, that means the dotted line passes through it, which means the true parameter of 10 is captured by the interval. So there is one red interval. It was a sample of 10 that produced an interval that did not capture the parameter. It did not capture mu. If I hit go again, it does 10 new ones. All 10 of them are green. They all caught it. You can see the running total right underneath that where it says 20 out of the 21 have captured it so far. You can just do 10 at a time if you want. 10 more green ones. Ooh, 10 more green ones. If you get bored doing this, well, a lot of green ones. Oh, wait, there's 3 red ones. But if you get bored, you can just say, let's speed this up a little bit. I want to do 100 random samples. Now it's going to get kind of crowded here, but when I hit go, boop, there's 100 of them. And you can pretty quickly see the red ones. I see 1, 2, 3, 4, 5, 6. So that means 94 of them are green and 6 of them are red. So that's a 94% success rate, which again, I've set this at up here. I set it at 95%. So that's not bad for 100 random samples. So I thought this might be something you could play around with for a little while. You could change this to 1,000, which is going to get crazy because it's going to try to show you 1,000 green intervals. Well, mostly green and some red. It's going to get really busy on the eyes. So yeah, almost impossible to really see what's going on. But you can at least see the breakdown. You can see the percentage of our samples that are green, and it says 94.7. So pretty close to our 95%. Okay, so that is what we know about confidence intervals after this. Good luck with your work. Thanks, thanks, thanks.